Right now, as you settle into the warmth of your evening, in the coldest, driest place on Earth, a glacier is bleeding, not metaphorically, not poetically, but visibly, crimson water pouring from pristine white ice, staining the frozen landscape the color of rust and blood. This is Blood Falls, a 5-story cascade of red water flowing from the Taylor Glacier in Antarctica's McMurdo dry valleys. When explorers first discovered it in 1911, they thought they were witnessing algae blooms, but the truth, discovered over a century of investigation, is far stranger. A glimpse into an alien world that's been sealed beneath ice for 2 million years, where life exists in ways that shouldn't be possible. Perhaps you're wrapped in a blanket, a cup of something warm nearby, surrounded by the comfortable signs of life: oxygen to breathe, warmth to maintain your body temperature, food within reach. But beneath Antarctica's Taylor Glacier, in a hidden lake that hasn't seen sunlight since before humans existed, microbes thrive in conditions that would kill most life instantly. No oxygen, no light, temperatures below freezing, and water 3 times saltier than the ocean. These aren't just surviving, they're thriving, creating their own ecosystem, their own chemistry, their own rules for existence. And every few years, when conditions align, this hidden world bleeds through the glacier, offering us a glimpse of life as it might exist on other planets, in other impossible places. Tonight, we're going to journey to one of Earth's most alien landscapes, where water runs red, ice preserves secrets millions of years old, and life finds a way in the most impossible circumstances. We'll discover how this crimson cascade was created, what lives in the darkness beneath the ice, and what Blood Falls tells us about life's incredible ability to persist in the universe's most hostile corners. So, let your mind wander to the bottom of the world, to a place where temperatures drop to -60 degrees Celsius, where the sun doesn't rise for months, where a glacier bleeds ancient water the color of iron and rust, and prepare to discover one of our planet's most beautiful and bizarre phenomena. The McMurdo dry valleys of Antarctica are perhaps the most Mars-like place on Earth. This is a landscape that seems to belong to another planet, a frozen desert, where it hasn't rained for 2 million years, where winds can reach 200 miles per hour, where the average annual temperature is -20 degrees Celsius, and where the humidity is so low that any snow that falls sublimates directly into vapor, without ever becoming liquid. These valleys exist because of a geographical quirk. The Transantarctic Mountains block the flow of ice from the East Antarctic ice sheet, creating pockets of exposed ground in a continent otherwise buried under miles of ice. The valleys cover about 4,800 square kilometers, roughly the size of Rhode Island, making them the largest ice-free region in Antarctica. The landscape is primordial, apocalyptic, beautiful, bare rock sculpted by millions of years of wind, frozen lakes covered with ice, so thick it's measured in meters, ventifacts, rocks carved into strange shapes by wind-blown sand, and scattered throughout, the mummified remains of seals that wandered too far inland and died, preserved for thousands of years in the dry, cold air. It's here, in this alien landscape, that we find Taylor Glacier, a tongue of ice, extending from the East Antarctic ice sheet, down into Taylor Valley. The glacier is about 54 kilometers long, moving at the glacial pace of a few centimeters per year, and at its terminus, where the glacier meets the frozen surface of Lake Bonny, something extraordinary happens. On a cold day in 1911, Australian geologist Griffith Taylor was exploring the valley that would later bear his name. He was part of Robert Falcon Scott's Terra Nova expedition, the British venture to reach the South Pole that would end in tragedy. But before that ill-fated polar journey, Taylor and his team were conducting scientific surveys of the Antarctic coast. What Taylor found that day defied explanation. From a crevasse in the glacier flowed a stream of blood-red water, cascading down the white ice face and pooling on the frozen lake below. In his journal, Taylor wrote, "We came upon a curious phenomenon, a frozen waterfall of blood-red color, apparently flowing from the glacier. The sight was so unexpected, so impossible in this frozen desert, that Taylor and his team struggled to explain it. Their best guess was red algae, microscopic plants that can turn snow and ice pink or red, like watermelon snow found in alpine regions. It seemed the only logical explanation for water, the color of blood flowing from ancient ice. Taylor documented the falls, took samples, and moved on. He had no way of knowing he'd discovered one of Earth's most extraordinary ecosystems, a window into deep time, a natural laboratory that would take a century to understand. The falls were named after him, Blood Falls in Taylor Valley flowing from Taylor Glacier. For decades, Blood Falls remained a curiosity, a strange footnote in Antarctic exploration. The remote location, extreme conditions, and logistical challenges of Antarctic research meant few scientists could study it. Those who did confirmed it wasn't algae. But what it was remained a mystery. The story of Blood Falls begins not thousands but millions of years ago. During the Miocene epoch, between 5 and 15 million years ago, Antarctica was a different world. The continent was still cold, but the ice sheets were smaller. The dry valleys contained lakes and possibly even fjords connected to the ocean. Around 2 million years ago, the climate shifted. The East Antarctic ice sheet advanced, covering the valleys with ice. But in Taylor Valley, something unusual happened. As the glacier moved over a pocket of seawater, it sealed it off from the surface, creating a subglacial lake. This wasn't just any lake. It was a time capsule. The microbes living in that ancient seawater were suddenly cut off from the rest of the world. No sunlight, no fresh nutrients, no contact with the surface. They were sealed in darkness beneath 400 meters of ice, in water that couldn't freeze because of its extreme salinity. Over the next 2 million years, this trapped lake evolved into something unique. The water became a brine, 3 times saltier than modern seawater. The temperature stabilized at about -5 degrees Celsius, below the freezing point of pure water, but liquid because of the salt. And the microbes, with nowhere to go, and no new resources, had to adapt or die. Most died, but some found a way to live that had never been seen before. The color of Blood Falls is the first clue to its extraordinary chemistry. The red isn't from algae, or any biological pigment, it's rust. Iron oxide, to be precise, the same compound that turns old cars orange and gives Mars its reddish hue. But where does the iron come from? The answer lies in the bedrock beneath the glacier. The ancient lake sits on iron-rich rock, and over millions of years, the water has become saturated with iron in its reduced form, ferrous iron, or ferrous 2+. This form of iron is colorless when dissolved in water. When this iron-rich water reaches the surface at Blood Falls, it encounters oxygen in the air for the first time in millions of years. The ferrous iron instantly oxidizes to ferric iron, ferrous 3+, forming iron oxide, rust. The clear water turns blood red in seconds, a 2-million-year-old chemical reaction finally completing. It's like watching the ancient past oxidize before your eyes. The iron that colors Blood Falls was dissolved from rock when the lake was first sealed. It's been waiting in the darkness, preserved in its reduced state, for this moment of exposure. Every drop of red water is a message from deep time, finally delivered. The concentration of iron is extraordinary, about 17 times higher than in normal seawater. This isn't just iron-rich water. It's essentially liquid rust waiting to happen. The reaction is so immediate, so dramatic, that you can watch the water change color as it flows. But the color is just the beginning of Blood Falls' strangeness. When scientists finally analyzed the water in detail, they found something that shouldn't exist: a thriving ecosystem. In the subglacial lake beneath Taylor Glacier lives a community of at least 17 different types of microbes. These aren't dormant or barely surviving. They're actively metabolizing, reproducing, evolving. They've been doing so in complete darkness, without oxygen, for 2 million years. How is this possible? The microbes have developed a unique metabolic system, unlike anything else on Earth. Unable to use sunlight for photosynthesis or oxygen for respiration, they found another way to generate energy. They're eating the rock. Specifically, they're using sulfate SO4 as an oxygen substitute, combining it with iron from the bedrock in a complex chemical reaction that releases energy. The process, called chemosynthesis, is known from other extreme environments, but the blood falls microbes have taken it to a new level. They've created a closed-loop system. The microbes use sulfate to oxidize organic matter, producing sulfide. Then they use the sulfide to reduce ferric iron from the bedrock to ferrous iron, which releases more energy. The ferrous iron can then be reoxidized using sulfate, starting the cycle again. It's a metabolic perpetual motion machine, running for millions of years. To understand how extraordinary this is, consider what life normally requires. Almost all life on Earth ultimately depends on the sun. Plants use photosynthesis to convert sunlight into chemical energy. Animals eat plants, or other animals that eat plants. Even deep-sea creatures living in permanent darkness depend on organic matter that rains down from the sunlit surface. The blood falls ecosystem is different. It's a chemotrophic system. The microbes make their own food from inorganic chemicals, with no connection to photosynthesis. They're living proof that life doesn't need the sun. This has profound implications. If life can exist in the darkness beneath an Antarctic glacier, sustained only by chemical reactions with rock, where else might it exist? Europa, Jupiter's ice-covered moon, has a subsurface ocean that might harbor similar chemistry. Enceladus, Saturn's moon, spews water from underground seas. Mars might have subglacial lakes like the one beneath Taylor Glacier. Blood falls isn't just a terrestrial curiosity, it's a model for astrobiology, showing us how life might exist on other worlds. The microbes of blood falls belong to an exclusive club, organisms that have been isolated from the rest of life for millions of years. They're living fossils, but also living experiments in evolution. When scientists sequenced the DNA of blood falls microbes, they found something remarkable. These organisms are related to marine microbes, confirming the theory that the subglacial lake originated as trapped seawater. But 2 million years of isolation have changed them. The dominant microbe is a species called Microbes arctica, a sulfur-oxidizing bacterium, but it's not quite the same as its marine relatives. It's evolved unique adaptations to the extreme cold, high salinity, and complete darkness of its environment. Its enzymes work at temperatures that would shut down most life. Its cell membranes have special compositions to remain fluid in the cold. Its DNA repair mechanisms are enhanced to deal with damage from the harsh conditions. The community also includes iron-reducing bacteria that can switch between different metabolic pathways, sulfate-reducing bacteria that produce the sulfide others need, mysterious archaea, whose role in the ecosystem isn't fully understood, viruses that infect the bacteria, driving genetic exchange and evolution. This isn't just a collection of microbes, it's a functioning ecosystem with producers, consumers, and recyclers. Nutrients are precious in this closed system, so everything must be recycled. Dead cells are immediately consumed by others. Waste products from one species become food for another. It's an economy of scarcity perfected over millions of years. The population density is low by surface standards, about 1,000 to 10,000 cells per milliliter, compared to millions in seawater. But for an ecosystem with no external energy input, it's remarkably productive. The microbes have achieved a stable state, a balance between growth and death that has persisted for geological time. Blood falls doesn't flow continuously. It's an intermittent phenomenon, sometimes dormant for years, then flowing for weeks or months. Understanding why required decades of research and some surprising discoveries. The subglacial lake isn't a single large body of water, but a network of brine channels and pockets extending beneath the glacier. This brine network is like a circulatory system, with blood falls as its outlet. The flow is driven by a combination of factors: pressure, The weight of 400 meters of ice creates enormous pressure on the brine below. This pressure forces water through cracks and channels in the ice, eventually reaching the surface at blood falls temperature. The glacier ice is about -17 degrees Celsius, while the brine is at -5 degrees Celsius. This temperature difference creates a complex thermodynamic system. The relatively warm brine can melt channels through the colder ice, creating temporary pathways. Salinity. The extreme saltiness of the brine lowers its freezing point and increases its density. This dense brine can force its way through the glacier like oil through rock, finding weaknesses and exploiting them. Tides. Even in Antarctica, ocean tides affect the land. The subtle flexing of the glacier with tides might pump brine through the system, like a heart beating once every 12 hours. When conditions align, perhaps a slightly warmer period, a shift in glacier pressure, or a tidal pump, the brine breaks through at blood falls. The rust-red cascade might flow for days or months before the channel freezes closed again, sealing the ancient ecosystem back in darkness. Studying blood falls has required revolutionary techniques. The extreme conditions make traditional sampling nearly impossible. The water freezes instantly when collected. The microbes, adapted to high pressure and no oxygen, often die when brought to the surface. The remote location means every expedition costs millions of dollars. Scientists have developed extraordinary methods. Ice drilling, special drills that can penetrate hundreds of meters of ice without contaminating the samples. The drills are sterilized with hydrogen peroxide and UV light to avoid introducing surface microbes. In situ analysis. Instruments lowered into boreholes to analyze the brine in its natural state. These include cameras, chemical sensors, and even DNA sequencers that work in extreme cold. Geophysical imaging. Radio echo sounding to map the brine network beneath the glacier. The salty water reflects radio waves differently than ice, revealing the hidden plumbing system. Isotope analysis. Studying the ratios of different isotopes in the water and minerals to understand the age and origin of the system. Metabolic tracers. Adding labeled compounds to samples to track what the microbes are eating and producing. Each expedition to blood falls pushes the boundaries of polar science. Researchers must work in temperatures that freeze exposed skin in minutes, winds that can knock people over, and altitudes that leave them gasping for breath. Equipment fails in the cold, batteries die, samples freeze, yet they persist, drawn by the mystery of life in impossible places. Blood falls represents something unique in science. A natural experiment running for 2 million years. The subglacial lake is a closed system, isolated from external inputs, where evolution has proceeded independently from the rest of Earth's biosphere. This isolation makes blood falls invaluable for understanding evolution. How do organisms adapt when resources are finite? How does an ecosystem maintain stability over geological time? What are the minimum requirements for life? The microbes have answered these questions in surprising ways. Metabolic flexibility. Many microbes can switch between different metabolic pathways depending on available resources. When sulfate is abundant, they use it. When iron is available, they switch to iron metabolism. This flexibility is key to long-term survival. Extreme efficiency. Every atom of nutrient is precious. The microbes have evolved to waste nothing. Their cellular machinery is optimized for efficiency rather than speed. Genetic stability. Despite millions of years of isolation, the microbes haven't accumulated excessive mutations. They've found a balance between stability and adaptation. Cooperative evolution. The different species have evolved together, becoming interdependent. No single species could survive alone. They need the complete community. This 2 million year experiment shows that life, once established, is remarkably persistent. Even in the most extreme isolation, with minimal resources, life continues. It doesn't just survive, it thrives, evolves, and creates sustainable ecosystems. Blood falls has become a crucial analog for astrobiology, the study of potential life on other worlds. The conditions in the subglacial lake are remarkably similar to what we might find elsewhere in the solar system. Europa, Jupiter's moon. Europa has a global ocean beneath its icy crust. This ocean is dark, salty, and in contact with a rocky seafloor, much like the environment beneath Taylor Glacier. If microbes can thrive in Blood Falls brine, they might thrive in Europa's ocean. Enceladus, Saturn's moon. Enceladus shoots geysers of water into space from its subsurface ocean. Analysis of these geysers shows salt, organic compounds, and possibly hydrothermal activity. The chemistry is different from Blood Falls, but the principle is the same: life in dark, ice-covered water. Mars, the red planet, has polar ice caps and possibly subglacial lakes. In 2018, radar evidence suggested a lake beneath Mars's south polar ice cap. Could Martian versions of Blood Falls microbes live there? Titan, Saturn's largest moon, has lakes of liquid methane and ethane. While very different from water-based life, the Blood Falls ecosystem shows that life can use unexpected chemistry. Blood Falls teaches us to expand our definition of habitable. We used to think life required sunlight, moderate temperatures, and oxygen. Blood Falls proves none of these are necessary. Life needs only liquid water, chemical energy, and time. While Blood Falls has existed for 2 million years, it's now threatened by climate change. Antarctica is warming faster than most of Earth, and the dry valleys are particularly vulnerable. Rising temperatures could increase meltwater, diluting the brine-change glacier dynamics, potentially closing the outlet, alter the chemical balance that sustains the ecosystem, introduce oxygen, poisoning the anaerobic microbes. Blood Falls has survived ice ages and interglacials, but the current rate of change is unprecedented. We might be witnessing the last centuries of this 2 million year phenomenon. There's deep irony here. Blood Falls shows life's incredible resilience, surviving conditions that would kill most organisms instantly. Yet it might not survive human-caused climate change. The ecosystem that endured millions of years of isolation could be destroyed by a few degrees of warming. Scientists are racing to study Blood Falls while it remains pristine. Every sample, every measurement, every DNA sequence is precious. We're archiving a 2 million year old ecosystem before it potentially disappears. Blood Falls challenges our assumptions about life's requirements and limitations. It forces us to think differently about what life is and what it needs. Life without sun. Almost all Earth's ecosystems ultimately depend on photosynthesis. Blood Falls doesn't. It's powered by geology, not biology. This independence from the sun means life could exist in places we never imagined, inside planets, in interstellar space, anywhere with the right chemistry. Life in isolation. The Blood Falls ecosystem has been isolated for longer than humans have existed. It shows that life doesn't need genetic exchange with other populations, doesn't need new resources, doesn't need change. Stability can persist for geological time. Life as chemistry. The microbes of Blood Falls are essentially biological machines for facilitating chemical reactions. They've evolved to be catalysts, speeding up reactions that would otherwise take millennia. Life becomes a way for chemistry to happen faster. Life as information. Despite isolation, the microbes maintain their genetic information across millions of years. Their information preservation systems, keeping instructions for life safe in the most extreme conditions. These philosophical implications extend beyond biology. If life can exist in Blood Falls conditions, what else is possible? What other impossible things might be real? I first learned about Blood Falls through a grainy photograph in a geology textbook. The image was shocking, a cascade of red against white, looking like a wound in the glacier. The caption was minimal: iron-rich water emerging from Taylor Glacier, Antarctica. But that image haunted me. How could water flow in Antarctica? Why was it red? What was the source? The textbook didn't say, and this was before easy internet searches. Blood Falls became a mystery I carried, a question mark in my understanding of the world. Years later, in graduate school, I attended a lecture by a researcher who had actually visited Blood Falls. She showed slides of the approach, helicopter landing on a frozen lake, hiking across ice toward the glacier. Then suddenly this cascade of red. She described the smell, metallic, like pennies, the sound, a gentle gurgle, surprising in the Antarctic silence. But what struck me most was her description of taking samples. The water, she said, was alive. This ancient brine, sealed for 2 million years, was teeming with microbes. They were breathing iron, eating sulfur, thriving in conditions that would instantly kill most life. It was like discovering aliens on Earth. Blood Falls has become, for me, a meditation on persistence. The microbes beneath Taylor Glacier have survived longer than any human civilization, longer than our entire species. They've persisted through unimaginable isolation, with resources that would seem impossibly inadequate. Yet they don't just survive, they thrive. They've created a sustainable ecosystem, a balance that has lasted millions of years. They've found equilibrium in the most unlikely place. There's a lesson here about life's tenacity. When we think conditions are impossible, life finds a way. When we think resources are too limited, life adapts. When we think isolation is deadly, life creates its own world. This isn't toxic positivity or empty inspiration. The Blood Falls microbes succeeded because they fundamentally changed, adopting entirely new metabolisms, new relationships, new ways of being. Survival required transformation. There's strange beauty in Blood Falls. The visual is arresting. Red water on white ice, rust on snow, warmth-colored flow in a frozen world. It's a paradox made visible, an impossibility you can photograph. But the deeper beauty is in the story. An ancient ocean, trapped and transformed. Microbes adapting to darkness, creating their own energy from rock. A glimpse of deep time bleeding through glacier ice. It's poetry written in chemistry, an epic tale told by bacteria. I've never visited Blood Falls in person. Few have. The location is too remote, too expensive, too logistically challenging. But I've spent hours studying photos, reading papers, watching the rare videos. Each time I'm struck by how alien it looks, like a landscape from another planet bleeding onto ours. Blood Falls has captured imaginations beyond science. Science fiction. Authors use Blood Falls as inspiration for stories about alien life, hidden ecosystems, and ancient mysteries. The image of bleeding ice is too powerful to ignore. Documentaries, nature programs feature Blood Falls as Earth's most alien landscape. The visual drama combines with scientific mystery for compelling television. Art. The striking visual has inspired paintings, photographs, and installations. Artists explore themes of isolation, persistence, and hidden life. Music. Composers have created pieces inspired by Blood Falls, using the sound of flowing water, the rhythm of bacterial metabolism, the 2 million year silence. The name itself, Blood Falls, ensures memorability. It's visceral, slightly disturbing, immediately intriguing. You can't hear Blood Falls without wanting to know more. While no indigenous peoples live permanently in Antarctica, the continent holds cultural significance for Southern Hemisphere indigenous groups. Some Maori traditions speak of Hui Teranjora, a 7th century navigator, who may have reached Antarctic waters, describing frozen seas and white rocks that grow from the sea. The idea of blood flowing from ice resonates with many indigenous traditions about the land being alive, having blood, breathing. Blood Falls becomes a literal manifestation of these metaphors, the earth bleeding, the glacier alive. Some indigenous scholars see Blood Falls as confirmation of traditional knowledge, that the land is more alive than Western science traditionally acknowledged. The discovery of life, in impossible places, validates worldviews that see life force in all things. So Blood Falls has become a powerful teaching tool. Extremophiles. It's the perfect example of life in extreme conditions, more accessible than deep-sea vents, more dramatic than hot springs. Evolution, the 2 million year isolation, provides a clear example of evolution in action. Adaptation to unique conditions. Chemistry. The iron oxidation is visible chemistry, a reaction you can see and understand. Climate science. The threat to blood falls from climate change makes global warming tangible and immediate. Astrobiology. Students can imagine life on other worlds by studying life in Earth's most alien environment. Teachers use blood falls to spark curiosity. The initial reaction, water can't flow in Antarctica, leads to questions, research, discovery. It's a gateway to understanding extremophiles, biogeochemistry, and the possibility of extraterrestrial life. Research at blood falls continues, with several major projects. The MIDGE project, minimally invasive, direct glacial exploration, uses a special drill to sample the subglacial brine without contamination. The goal is to study the microbes in their natural state. Blood falls metabolomics, analyzing all the small molecules in the brine to understand the complete chemistry of the ecosystem. Time series monitoring, continuous monitoring of flow, temperature, and chemistry, to understand what triggers bleeding events. Genomic evolution study, comparing blood falls microbes to their closest relatives to understand 2 million years of isolated evolution. Analog mission testing, using blood falls as a testing ground for instruments that might one day search for life on Mars or Europa. Each field season brings new discoveries. Recent findings include previously unknown metabolic pathways, viruses that infect the bacteria and drive evolution, trace gases that might be detectable on other planets, mineral formations that preserve evidence of past life. New technology is revolutionizing blood falls research. Environmental DNA sampling, collecting and analyzing DNA from the water without cultivating microbes, revealing organisms we can't grow in labs. Nanosensors, tiny sensors that can operate in the brine channels, transmitting data about conditions we've never been able to measure. Ice-penetrating robots, autonomous devices that can explore the subglacial network, mapping the hidden world beneath Taylor Glacier. Isotope analysis. New techniques for analyzing isotopes reveal the age of the water, the source of nutrients, and the metabolic processes occurring. Machine learning. AI systems, analyzing the complex interactions in the ecosystem, finding patterns humans might miss. These technologies are expanding our understanding while minimizing impact on this unique ecosystem. Blood falls is protected as part of an Antarctic Specially Protected Area, ASP. Strict protocols govern research, limited number of visits per year, sterile sampling techniques to avoid contamination, minimal physical disturbance, complete removal of all waste, detailed documentation of any changes. The goal is to preserve blood falls for future research, while learning as much as possible. It's a delicate balance, studying an ecosystem without destroying it. There's also discussion about enhanced protection as climate change accelerates. Should blood falls be given the highest level of protection? Should we limit research to preserve it? These questions have no easy answers. Blood falls isn't unique. Antarctica has over 400 known subglacial lakes, each potentially harboring life. The most famous is Lake Vostok, buried under 4 kilometers of ice, isolated for perhaps 15 million years. Each lake is a potential blood falls, a hidden ecosystem waiting to be discovered. Some might use different chemistry, methane metabolism, hydrogen oxidation, or processes we haven't imagined. Each is a natural experiment in isolation and adaptation. The techniques developed at blood falls are being applied to these other lakes. The lessons learned about contamination, sampling and analysis guide exploration of Earth's last frontiers. But blood falls remains special because it's accessible. The brine reaches the surface naturally, offering a window into the subglacial world. Other lakes require drilling through kilometers of ice, risking contamination and environmental damage. Blood falls is becoming a climate change sentinel. Changes in flow patterns, chemistry, and temperature provide early warning of Antarctic warming. Recent observations show increased flow frequency, possibly due to glacier melting, slight dilution of the brine, suggesting meltwater infiltration. changes in microbial community composition, new minerals precipitating as chemistry shifts. These changes are subtle but significant. Blood falls has been stable for 2 million years. Any change is noteworthy. The ecosystem that survived ice ages might not survive human-caused warming. This paradox, extreme resilience meeting rapid change, encapsulates our climate crisis. The blood falls microbes have unique properties valuable for biotechnology. Extreme enzymes, proteins that work at freezing temperatures, could revolutionize cold storage, food processing, and industrial chemistry. Novel metabolisms. The iron-sulfur metabolism might enable new ways to process industrial waste or generate energy. Antifreeze compounds, molecules that keep the brine liquid at -5 degrees Celsius, could improve organ preservation, cryogenics, and cold weather operations. DNA repair systems, mechanisms that maintain genetic integrity for millions of years, could improve data storage and cancer treatment. Closed-loop ecosystems. The self-sustaining ecosystem model could guide design of life support systems for space travel or underground cities. Several companies are already investigating blood falls-inspired technologies. The microbes that lived in isolation for 2 million years might help solve 21st century problems. Blood falls forces us to reconsider what life is. Life as process. The blood falls ecosystem is less about individual organisms and more about chemical processes perpetuating themselves. Life becomes a verb, not a noun. Life as information. The genetic information has persisted for 2 million years, despite the death and replacement of countless individuals. DNA becomes the true survivor. Life as community. No single species could survive alone. Life exists only as interconnected networks, not isolated entities. Life as patience. The microbes wait years between cell divisions. Life becomes about persistence, not proliferation. These perspectives challenge anthropocentric views of life, based on human timescales and experiences. Blood falls operates on different temporal scales. Bacterial time. Individual microbes living for years or decades, reproducing slowly. Ecological time. The ecosystem maintaining balance for millions of years. Ecological time. The glacier moving, the lake evolving, the chemistry changing over eons. Human time. Our brief visits, our century of study, our fleeting observations. Cosmic time. The brief moment in universe history when conditions allow blood falls to exist. These nested timescales remind us of our temporal provincialism. We judge permanence by human lifespans, but blood falls shows other ways of being in time. Blood falls was discovered in 1911, but it existed for 2 million years before. This raises questions about discovery. Does something exist meaningfully before humans know about it? How many blood falls remain undiscovered? What is lost when ancient phenomena are discovered and studied? Who has the right to name and claim natural wonders? The colonial context of Antarctic exploration adds complexity. Blood falls was named by British explorers, studied by Western scientists, its story told in English. Other cultural perspectives might see and understand it differently. In the coming years, we can expect complete mapping. The entire subglacial network beneath Taylor Glacier will be mapped using ice-penetrating radar and robotic exploration. Metabolic understanding. Every chemical reaction in the ecosystem will be cataloged, creating a complete picture of the energy economy. Genomic timeline. DNA analysis will reveal the evolutionary history, showing how organisms adapted over 2 million years. Climate impacts. Will document how climate change affects this ancient ecosystem, possibly witnessing its transformation or destruction. Technological applications. Blood falls-inspired technologies will reach market, from antifreeze proteins to closed-loop life support systems. Looking ahead decades or centuries, preservation or loss. Blood falls might be preserved through heroic conservation efforts, or it might cease to exist as we know it, diluted and oxygenated by climate change. Off-world discoveries. Missions to Europa or Enceladus might find their own versions of blood falls proving life exists beyond Earth. using similar chemistry, synthetic ecosystems. We might recreate blood falls-like ecosystems artificially, using them for waste processing, energy generation, or life support. Deep drilling. Advanced technology might allow us to explore the source lake directly without contamination, revealing new organisms and chemistry. Cultural evolution. Blood falls might become a pilgrimage site, a symbol of life's persistence, a monument to what we've lost or preserved. Blood falls raises profound questions that may never be fully answered. How many isolated ecosystems exist on Earth? What is the minimum requirement for life? Can consciousness emerge from chemical cycles? Is the universe filled with blood falls on other worlds? What is our responsibility to ecosystems we've just discovered? These questions push the boundaries of science, philosophy, and ethics. As we near the end of our journey to blood falls, consider what we've discovered. A wound in Antarctic ice that bleeds ancient seawater colored red by iron, that last saw oxygen when our ancestors were barely human. In this blood lives an ecosystem older than imagination, thriving in conditions that would kill us in seconds. Blood falls is Earth bleeding history, weeping time, showing us its hidden life. It's a reminder that our planet is more alive than we know, in places we never thought to look, in ways we never thought possible. The red cascade is beautiful and terrible, natural and alien, ancient and immediate. It exists at the intersection of deep time and present moment, geological patience and bacterial persistence, cosmic cold and chemical energy. Blood falls teaches us that impossible is a limited concept. Water flowing in Antarctica seemed impossible. Life without sunlight seemed impossible. Ecosystems isolated for millions of years seemed impossible. Yet all are real, documented, studied. What other impossibilities might be real? What assumptions about life, Earth, and the universe might be wrong? Blood falls invites us to expand our conception of possible, to look for life in unlikely places, to expect wonders in the most hostile environments. This isn't optimistic thinking but scientific observation. Nature repeatedly exceeds our expectations, not through magic, but through patient adaptation, chemical creativity, and deep time. Imagine the blood falls microbes in their dark, cold, salty world. For 2 million years, they've lived without sun, without sky, without change, except what they create themselves, generation after generation, dividing slowly, metabolizing iron and sulfur, maintaining their community. They don't know they're remarkable. They don't know scientists study them, that they might hold keys to finding life on other worlds, that they've survived longer than mountain ranges. They simply persist, processing chemicals, maintaining balance, continuing. There's a deep peace in this persistence. No urgency, no crisis, just patient continuance. The microbes teach us that life doesn't require drama, progress, or purpose beyond existence itself. Sometimes, persistence is enough. Blood falls connects to everything. The iron that colors it formed in stellar cores. The water molecules have been recycling through Earth's systems for billions of years. The microbes share ancestry with all life on Earth. The glacier that seals them is made of snow that fell when Earth's climate was different. We're connected too. The oxygen we breathe would kill blood falls microbes, but we share DNA sequences. The iron in our blood is the same element that makes blood falls red. We're part of the same Earth system, the same cycling of elements, the same persistence of life. Understanding blood falls helps us understand ourselves, how we're both unique and connected, both fragile and persistent, both impossible and inevitable. Blood falls will continue bleeding, perhaps for years, perhaps for centuries. Climate change might end its flow, or it might persist against our expectations. The microbes will continue their patient metabolism until conditions change beyond their tolerance, or until the sun expands and Earth becomes uninhabitable, or until something unimaginable happens. Future scientists will study blood falls with tools we can't imagine, answering questions we don't know to ask. They might find new organisms, new chemistry, new impossibilities, or they might find blood falls gone, existing only in samples and data, a monument to what Earth once was. Either way, Bloodfalls has already given its gift, proof that life transcends our limitations, that Earth holds wonders in its most forbidding places, that 2 million years of isolation can create something beautiful and terrible, and absolutely real. Picture bloodfalls one last time, red water emerging from white ice, impossible made visible, ancient made present. The cascade flows down the glacier face, pooling on frozen Lake Bonny, oxidizing in Antarctic air. Microbes that haven't seen sunlight for 2 million years, suddenly exposed, their iron blood painting the ice. It's a glimpse into deep time, a window into alien chemistry, a reminder of life's creativity. It's Earth showing us its hidden circulation, its secret metabolism, its capacity for surprise. It's beautiful because it shouldn't exist, remarkable because it does. As you drift towards sleep tonight, perhaps you'll dream of bloodfalls. In your dreams you might stand before the glacier, watching red water flow, smelling the metallic tang of iron, feeling the Antarctic cold. You might imagine the darkness beneath the ice, where microbes slowly process chemicals, maintaining their ancient balance. Or you might dream of other impossible places where life thrives, deep ocean vents, inside rocks, in clouds, between ice crystals. Bloodfalls has taught us to look for life everywhere, to expect it in the most unlikely places, to never say impossible. Bloodfalls will bleed tomorrow, or next year, or next century. The microbes will continue their patient chemistry, cycling iron and sulfur, maintaining their community in darkness. The glacier will creep forward, the brine will flow through its channels, the ancient ecosystem will persist. We've witnessed something extraordinary, life at the edge of possibility, thriving where it shouldn't exist, persisting through unimaginable time. Bloodfalls has shown us that Earth is more alive than we knew, in ways we never imagined, in places we never thought to look. The blood of the glacier is the blood of time, the blood of persistence, the blood of life itself, refusing to surrender even in the most impossible circumstances. It flows not because it must, but because it can, because after 2 million years of darkness, the ecosystem found a way to bleed through to the light. Sleep now, knowing that somewhere in Antarctica, a glacier is bleeding ancient water. Somewhere beneath ice, microbes are metabolizing iron. Somewhere in darkness, life persists. Bloodfalls continues its patient flow, marking time in rust and brine, writing its story on ice. The impossible cascade continues. The blood of deep time flows on. The miracle of persistence endures. And perhaps that's the final lesson of bloodfalls. Not that life is fragile, but that it's incredibly, impossibly, beautifully persistent. Even in the coldest, darkest, most isolated places on Earth, life finds a way. The glacier bleeds, the microbes thrive, the impossible becomes real. Bloodfalls flows on, red against white, warm-colored in a frozen world, life persisting against all odds, bleeding through ice, through time, through impossibility itself. The blood continues to fall. To truly understand the discovery of bloodfalls, we need to understand the heroic age of Antarctic exploration. Griffith Taylor wasn't just wandering Antarctica randomly, he was part of one of history's most ambitious and ultimately tragic expeditions. Robert Falcon Scott's Terra Nova expedition, 1910 to 1913, had multiple objectives: to be first to the South Pole, to conduct extensive scientific research, and to map unexplored regions of Antarctica. While Scott would famously lose the race to the pole to Roald Amundsen and die on the return journey, the expedition's scientific achievements were extraordinary. Taylor led the Western Geological Party, tasked with exploring the Dry Valleys region. These men were doing science in conditions that would defeat most modern expeditions. They had wool clothing, canvas tents, and rudimentary equipment. No helicopters, no satellite phones, no modern cold weather gear. They man-hauled sledges weighing hundreds of pounds across ice and rock, conducting detailed geological surveys while fighting hypothermia and frostbite. When Taylor first saw bloodfalls on January 1911, He was already exhausted from weeks of exploration. His journal entry that day is understated, almost British in its restraint. Curious red staining on the glacier face. Appears to be water flow, though this seems impossible in these temperatures. Collected samples for analysis. Taylor had no idea he'd discovered something that would still be studied over a century later. To him, it was one curiosity among many in a land full of impossibilities. The team spent only a few hours at the site, taking photographs with their heavy plate cameras, collecting water samples in bottles that would take months to reach laboratories in England. Here, quote, as a detail rarely mentioned in Bloodfall's stories, Taylor's original samples were nearly lost. After collection, they were cached with other geological specimens for later retrieval. But Antarctic logistics are unforgiving. Some caches were never recovered, buried by snow or lost when sea ice broke up. Taylor's Bloodfall samples survived by luck. They were retrieved by a later party and shipped to England on the Terra Nova. But the ship nearly sank in a storm off New Zealand. Water flooded the holds where specimens were stored. Many samples were destroyed or contaminated. The Bloodfall samples that reached London were already compromised. The iron had oxidized completely. Any microbes were long dead. The chemical analysis showed high iron content and unusual salinity, but the true nature of Bloodfalls remained hidden. It would take another century and vastly better technology to understand what Taylor had found. After the Terra Nova expedition, Bloodfalls was largely forgotten. Antarctica itself was barely visited for decades. The site was too remote, too expensive, too dangerous for follow-up studies. It existed mainly in Taylor's photographs and notes. A footnote in expedition reports that few people read. World War I, the Great Depression, World War II, global events, pushed Antarctic exploration to the margins. Bloodfalls became a curiosity mentioned in geology textbooks, usually with the wrong explanation. Most sources through the 1950s still claimed it was red algae, despite no evidence for this. The International Geophysical Year, 1957 to 1958, renewed interest in Antarctica. Nations established permanent research stations. New technology, aircraft, tracked vehicles, better cold weather equipment, made the continent more accessible. But Bloodfalls remained unstudied. It wasn't near any base, wasn't on any regular flight path, wasn't anyone's priority. Let's dive deeper into the extraordinary metabolism of Bloodfalls microbes. The chemical reactions they perform would be impossible in most environments, but the unique conditions beneath Taylor Glacier create a natural laboratory for extreme biochemistry. The primary energy cycle works like this. Organic carbon oxidation, ancient organic matter, trapped when the lake was sealed, provides carbon. Microbes oxidize this using sulfate instead of oxygen. Organic matter, plus SO4 CO2, plus H2S plus energy, sulfide oxidation. Sulfide produced is then oxidized using iron. H2S fel ses 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 Felses, 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 Furso-4 compounds cycle between oxidized and reduced. Sulfur compounds cycle between oxidized and reduced states. Ses, Furso-4 ses, H2S energy. This creates a closed loop where iron and sulfur cycle between oxidation states, extracting energy from ancient organic matter without depleting any single resource. It's like a metabolic perpetual motion machine. Though it does slowly consume the organic carbon, the efficiency is extraordinary. In normal environments, microbes waste significant energy, but Bloodfalls microbes can't afford waste. They've optimized every reaction, every enzyme, every cellular process for maximum efficiency. A single cell might divide only once per year, using energy that surface bacteria would burn through in minutes. DNA analysis of blood falls microbes reveals fascinating adaptations. Cold shock proteins, genes for proteins that prevent ice crystal formation inside cells. These proteins wrap around DNA and RNA, protecting them from cold damage. Osmotic stress genes. The extreme salinity would dehydrate normal cells. Blood falls microbes have multiple copies of genes for osmolyte production, small molecules that balance salt concentration. DNA repair systems. Radiation from radioactive decay in rocks damages DNA. The microbes have enhanced repair mechanisms, some unique to this ecosystem. Metabolic flexibility genes. Multiple pathways for energy generation, with switch mechanisms that respond to resource availability, like having several different engines in one car. Ancient genes. Some genes appear to be living fossils, versions that existed 2 million years ago but have since evolved differently in other organisms. These provide glimpses into ancient microbial life. The population genetics are unusual too. With no gene flow from outside populations, you'd expect reduced genetic diversity, but blood falls maintains surprising variety, possibly through high mutation rates in certain genes, gene transfer between species in the community, preservation of multiple gene variants that might be useful. Active DNA shuffling mechanisms. Recent discoveries have revealed viruses in blood falls bacteriophages that infect the bacteria. These aren't pathogens in the traditional sense but rather partners in the ecosystem's evolution. The viruses perform several roles: gene transfer, moving beneficial genes between bacterial species; population control, preventing any one species from dominating evolution driver; creating selection pressure for resistance; nutrient cycling. Cells release nutrients for others. The viruses themselves are extraordinary. They must remain viable in extreme cold and salt. Their DNA shows adaptations similar to the bacteria. Cold shock proteins, salt tolerance, DNA repair mechanisms. They've co-evolved with their hosts for 2 million years, creating a virus-bacteria ecosystem, unlike anything else on Earth. One fascinating observation: the viruses seem to have temperate life cycles, integrating into bacterial DNA rather than immediately destroying cells. This makes sense in a resource-limited environment. Destroying your host too quickly would be suicide. Instead, viruses wait for optimal conditions before activating. The liquid beneath Taylor Glacier isn't just salty water. It's a complex chemical soup, unlike any other natural water on Earth. Salinity: 3 times ocean water, approaching saturation for several salts. The dominant ions are chloride, chloride, sod, 150,000 mg cell, L sodium, nattert, sod, 90,000 mg cell, sulfate, soart, first sod, 15,000 mg cell, magnesium, mgesium, mg cell, 5,000 mg cell, calcium, K1g cell, 3,000 mg cell, iron. Concentrations reach 3,000 mg cell, compared to 1 mg cell, in typical groundwater. Multiple oxidation states exist simultaneously. Fulward, furous dominant in the brine. Fulward, furous one when exposed to oxygen. Iron sulfides precipitated as black minerals. Iron oxides, the rust that gives blood falls its color. Nutrients: despite isolation, essential nutrients persist. Nitrogen, mostly as ammonium. NH fluoride, were cycled from dead cells. Phosphorus, from rock weathering and cellular recycling. Trace elements, weathered from surrounding rocks. Gases, dissolved gases reveal the metabolism. No oxygen, O2 completely. Anaerobic carbon dioxide, SOD2 from respiration. Hydrogen, sulfide H2S from sulfate reduction. Methane TH4 trace amounts from unknown source. Hydrogen, H2 possibly from rock-water reactions. Page. around 6.2, slightly acidic, despite the marine origin. This is maintained by the balance of different chemical reactions. When blood flows, complex chemistry occurs as the brine meets surface conditions. Immediate reactions, immediate reactor second 4 seconds, immediate reactor second 4 second 4 second 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 second. Mineral formation. Various sulfates crystallize. Secondary minerals. Over days to weeks. Jarosite. Ka-Fe. 3. So4. 2. OH6. A yellow mineral. Gypsum. Ka-So4. 2H2O. Clear to white crystals. Halite. Nakiate. OHEA6. So4. An orange mineral. Minerals create the colorful deposits around blood falls, not just red, but yellow, orange, white, and even green. Each color tells a chemical story, a reaction frozen in mineral form. The glacier ice around blood falls is chemically unique. Brine channels. Microscopic channels of liquid brine penetrate the ice, creating a three-dimensional network. These channels are kept liquid by salt depression of freezing point, pressure from ice weight, heat from microbial metabolism, possible antifreeze proteins, ice composition. The glacier ice shows chemical gradients. Pure ice, far from brine channels. Salt-enriched ice, near channels. Iron-stained ice, where brine has penetrated. Mineral inclusions from precipitates. Cryoconcentration. As water freezes, salts are excluded, concentrating in remaining liquid. This creates microenvironments with extreme chemistry. Some channels might be saturated with specific salts, creating unique conditions for specialized microbes. Studying blood falls involves extraordinary logistical challenges. Access. No roads lead to blood falls. Researchers must fly to McMurdo Station, via New Zealand, helicopter, to Lake Bonny Camp, weather permitting, hike across frozen lake to glacier, several kilometers, all while carrying equipment in extreme cold weather windows. Research is possible only during Antarctic summer, October-February. Even then, temperatures range from -30 degrees Celsius to -5 degrees Celsius. Katabatic winds can exceed 100 miles per hour. Whiteout conditions can last days. Helicopter flights often canceled. Equipment challenges. Standard equipment fails in Antarctic conditions. Batteries die rapidly. Liquids freeze instantly. Metal becomes brittle. Electronics malfunction. Sample containers crack. Safety concerns. Medical evacuation might take days. Hypothermia risk. Constant frostbite can occur in minutes. Altitude sickness. Taylor Valley is at elevation. Crevasse danger on glacier. Carbon monoxide poisoning intense. Collecting samples from blood falls without contamination is extraordinarily difficult. Surface contamination. The moment brine emerges, it's contaminated. Oxygen exposure kills anaerobic microbes. Temperature change shocks cells. Pressure change causes cell damage. Oxidation alters chemistry. Sterile technique. In extreme cold, sterile sampling is nearly impossible. Gloves freeze to equipment. Sterile wrappings become brittle. Wind blows contaminants everywhere. Ice forms on every surface. Sample preservation. Keeping samples viable for analysis. Must maintain anaerobic conditions. Keep at sub-zero temperatures. Prevent freezing damages cells. Transport without vibration. Analyze quickly, before degradation. Scientists have developed specialized techniques. Triple-contained sampling devices. Argon gas flushing to remove oxygen. specialized preservatives that work at low temperature, portable analysis equipment for field measurements. Analyzing blood falls samples presents unique difficulties, low biomass. Microbial concentrations are low. Standard techniques need modification. Long incubation times required. Signal-to-noise ratio problems. Contamination has larger impact. Extreme chemistry. The brine's composition interferes with analysis. High salt precipitates in instruments. Iron interferes with DNA extraction. Cold temperatures affect enzyme reactions. pH changes during analysis. Slow growth. Microbes grow extremely slowly. Cultures take months to years. Many organisms won't grow in labs. Difficult to study. Metabolism. Hard to maintain proper conditions. Mixed communities, multiple species. Complicate analysis. Can't separate organisms easily. Metabolisms are interdependent. Community interactions. Essential single species. Studies impossible. Blood falls is part of a vast hidden hydrological system beneath Antarctic ice. Connected systems. Recent radar surveys reveal channels connecting multiple subglacial lakes, water moving between reservoirs, possible continent-wide circulation, exchange of water, nutrients, and possibly organisms. Other outlets. Blood falls isn't unique. Several glaciers show iron staining. Some have clear water outflows, others might be sealed but detectable. Each potentially harbors unique ecosystems. Lake Vostok connection. The famous subglacial lake might connect to blood falls system. Similar isolation times, comparable chemistry in some aspects. Possible shared microbial ancestors, parallel evolution in isolation. West Antarctic systems. Beneath the West Antarctic ice sheet. Active volcanism provides heat. Geothermal systems might support life. Different chemistry from blood falls. Potentially more diverse ecosystems. Blood falls has become crucial for Mars exploration. Recurring slope lineae. Dark streaks on Martian slopes might be briny water like blood falls, iron-rich like the outflow harboring. Similar. Microbes. Seasonal like blood falls, intermittent flow. Martian subsurface. Mars likely has subglacial lakes beneath polar caps. High salinity water preventing freezing. Iron-rich geology. Possible chemical energy sources. Life detection. Blood falls teaches us where to look for Martian life, what biosignatures to seek, how to sample without contamination, what instruments we need. Planetary protection. Blood falls demonstrates how easily contamination occurs, need for strict protocols, importance of pristine samples, risks of forward-backward contamination. Blood falls provides models for life on ice-covered moons. Europa, Jupiter's moon, global ocean, beneath ice crust, possible hydrothermal vents, salt water in contact with rock, chemical energy from radiation. Blood falls shows life is possible. Enceladus, Saturn's moon, geysers suggest subsurface, ocean organic compounds detected, energy from tidal heating, similar to blood falls but warmer, more diverse chemistry possible. Titan, Saturn's moon, possible subsurface water, ocean methane, ethane, surface lakes, complex organic chemistry, different from blood falls, but comparable. Isolation, expands, habitability concepts, Ganymede, and Callisto, Jupiter's moons, possible subsurface oceans, less energy available, more like blood falls conditions. Chemical energy might suffice, life would be slow, efficient. Despite its simplicity, blood falls has a functioning food web. Primary producers, chemosynthetic bacteria that fix carbon from CO to generate organic matter, use iron sulfur for energy, form ecosystem base. Primary consumers, heterotrophic bacteria that consume organic matter, break down dead cells, recycle nutrients, cannot make own food. Decomposers, specialized bacteria that break down complex molecules, release simple nutrients, complete nutrient cycles, prevent accumulation of waste. Viruses act as population controllers. Gene transfer agents, nutrient recyclers. via lysis, evolution drivers, scavengers, organisms that consume cellular debris, recycle rare elements, clean up metabolic waste, maintain system efficiency. This food web has persisted for 2 million years, with no external input, except minerals from rock weathering. Organisms in blood falls depend on each other. Metabolic coupling. One organism's waste is another's food. Sulfate reducers produce sulfide. Sulfide oxidizers consume it. Iron reducers produce fernord. Iron oxidizers use it. Nutrient sharing. Limited nutrients are shared. Nitrogen fixed by some, used by all. Vitamins produced and exchanged. Amino acids recycled communally. Trace elements distributed. Biofilm. Communities. Organisms live in structured communities. Physical proximity enables exchange. Protected microenvironments. Concentrated enzymes. Shared protective mechanisms. Quorum sensing. Chemical communication. Coordinates. Metabolic switching. Biofilm formation. Nutrient sharing. Stress responses. This cooperation is essential. Competition would destroy the system. 2 million years of isolation created unique evolutionary pressures. Resource limitation. Extreme selection for efficiency. Every atom counts. No waste tolerated. Maximum extraction from resources. Slow, careful growth. Stability selection. Changes are risky. Conservative. Evolution. Maintain what works. Small improvements only. Avoid disrupting balance. Community selection. Individual success means community success. Genes that benefit community spread. Selfish strategies eliminated. Cooperation enhanced. Interdependence deepened. Stress tolerance. Constant extreme conditions select for robust cellular machinery. Multiple backup systems. Stress response mechanisms. Cellular repair abilities. These pressures created organisms unlike any others on Earth. Beyond famous names, many researchers have dedicated careers to blood falls. Jill McCuckey, a microbiologist, who spent years perfecting techniques to study blood falls microbes. She describes first successfully culturing them. After 18 months of trying, seeing colonies finally grow was like watching impossible become possible. These organisms that had been isolated since before humans evolved were growing in my lab. Erin Pettit, a glaciologist, who studies how the brine moves through ice. She spent months camping on Taylor Glacier. You develop a relationship with the glacier. You learn its moods, its sounds. When blood falls flows, it's like the glacier is speaking. Alison Murray studies the molecular ecology, identifying organisms by DNA. Every sample reveals new species, new genes, new possibilities. It's like reading a book written in a language that's still being decoded. Peter Doran studies Lake Bonny, where blood falls terminates. The lake itself is stratified with different chemistry at different depths. Blood falls has been seasoning this lake for millennia, creating unique conditions. These scientists endure extreme hardship for moments of discovery. Behind every researcher at blood falls there's a support network. Helicopter pilots. Flying in Antarctica is dangerous. Rapid weather changes. No emergency landing sites. Mechanical failures mean death. Whiteout conditions common risk. Their lives for science. Field safety officers. Ensure researcher survival. Monitor weather constantly. Coordinate evacuations. Teach survival skills. Manage emergency response. Often former military or mountaineers. Laboratory technicians. Process samples at McMurdo. Work in cold labs. Maintain sterile conditions. Run analysis 24/7 during season. Critical but unrecognized logistics coordinators. Make research possible. Arrange complex supply chains. Coordinate international efforts. Navigate regulations. Solve impossible problems. Without them, no science happens. While no indigenous peoples inhabit Antarctica, the continent holds deep significance. Maori connections. Some Maori IWI tribes trace ancestral connections to Antarctic waters. T. Ranjora's voyage possibly reached Antarctic waters in 650 CE. Described Tioka, Apia, frozen sea, oral traditions, preserve navigation knowledge. Modern Maori scientists bring traditional knowledge to Antarctic research. South American indigenous views, peoples from Tierra del Fuego, have stories of southern ice spirits, lands beyond the Southern Ocean, connections between ice and life, balance between frozen and flowing, global indigenous perspectives on extreme environments. Inuit knowledge of ice ecosystems parallels Blood Falls Siberian people's understanding of permafrost life. Andean knowledge of extremophiles in high-altitude lakes all validate life in impossible places. These perspectives remind us that Western science discovers what indigenous knowledge has long suggested: life exists everywhere, even in the most extreme places. Blood Falls faces multiple threats: climate change, the most serious threat; regional warming, twice global average; increased meltwater could dilute brine; changed glacier dynamics might seal outlet; ecosystem disruption from temperature change; possible complete system collapse; research impact, even careful study causes damage; sampling removes irreplaceable material; equipment installation disturbs site; foot traffic compacts soil; helicopter downwash affects surface; cumulative impact over decades; tourism pressure, increasing visitor interest. Adventure tourism companies offer trips; photographers seek dramatic images; documentary crews want footage; each visit risks contamination, site degradation, accelerating pollution. Even in Antarctica, pollution arrives: atmospheric deposition of pollutants, microplastics in precipitation, research station emissions, aircraft exhaust, all affect chemistry. Current protection is inadequate, but improving. Antarctic Treaty System provides basic protection, prohibits military activity, ensures scientific freedom, bans nuclear testing, requires environmental assessment, but enforcement is weak. ASPA designation, Antarctic Specially Protected Area status, restricts access, requires permits for research, mandates minimal impact, but boundaries are limited, doesn't address climate change research protocols, self-imposed restrictions, minimal sampling, sterile techniques, leave no trace principles, data sharing to reduce redundancy, but not universally followed. Proposed enhancements, expand protected area boundaries, stricter permit requirements, ban non-scientific access, long-term monitoring program, international coordination improvement. Studying Blood Falls raises ethical questions: right to remain undisturbed. Should we study it at all? Research inevitably causes damage. Microbes can't consent to study. Ecosystem has intrinsic value. Knowledge versus preservation tension, ownership and access. Who decides? No country owns Antarctica. Scientists control access. Indigenous voices excluded. Commercial interests, growing benefit distribution. Who gains from discoveries? Patents on Blood Falls-derived compounds. Academic careers, built on research. Developing nations excluded. Traditional knowledge unrecognized. Future generations. What are we leaving? Degraded site for knowledge, contaminated ecosystem, climate change system, or preserved mystery. These ethical considerations challenge standard research practices. Current technology reveals Blood Falls secrets. Next generation DNA sequencing identifies organisms without cultivation. Illumina sequencing for diversity. PacBio for long reads. Oxford Nanopore for field sequencing. Metagenomics for community analysis. Transcriptomics for active genes. Mass spectrometry analyzes chemistry. ICP-MS for element concentrations. LC-MS for organic compounds. ML-DITO for proteins. Isotope ratio. MS for dating. High resolution for unknown compounds. Microscopy visualizes microbes. Cryo-electron microscopy for structure. Confocal for biofilms. Atomic force for surfaces. Fluorescence for specific organisms. Environmental SEM for in situ imaging. Spectroscopy studies minerals and chemistry. Raman for mineral identification. X-ray diffraction for crystal structure. NMR for organic molecules, FTIR for functional groups, Messbauer for iron species, geophysical methods, maps hidden, structure, ground-penetrating radar for channels, seismic for deeper structure, electrical resistivity for brine, magnetic surveys for iron, gravity for density variations. Each technique adds pieces to the puzzle. Understanding blood falls requires combining diverse data, multiomics, integration, genomics, DNA, transcriptomics, RNA, proteomics, proteins, metabolomics, small molecules, combined for system understanding, temporal datasets, changes over time, seasonal variations, annual patterns, decadal trends, linked to climate, predict future spatial, mapping, three-dimensional understanding, surface features, subsurface channels, vertical gradients, horizontal variation, connect to regional chemical biological correlation, link life to chemistry, who lives where, metabolic niches, chemical gradients, biological responses, system dynamics, model development, mathematical representation, metabolic models, population dynamics, chemical evolution, physical flow, predictive capacity. This integration reveals system-level understanding, impossible from individual measurements. The proteins produced by blood falls microbes are unlike anything else in nature. These molecular machines have evolved to function in conditions that would destroy normal proteins instantly. Consider what proteins normally need: moderate temperatures where they maintain their shape, reasonable salt concentrations that don't disrupt their charge balance, and liquid water to move and flex. Blood falls proteins work at -5 degrees Celsius in brine, 3 times saltier than seawater, with iron concentrations that would precipitate most proteins. The cold shock proteins are particularly remarkable. When normal cells encounter freezing temperatures, ice crystals form inside, puncturing membranes and destroying organelles. Blood falls microbes produce proteins that act as molecular antifreeze. These proteins don't prevent freezing entirely. That would require too much energy. Instead, they control ice crystal formation, ensuring crystals stay small and form between cells rather than inside them. One protein, tentatively named BFCSP1 blood falls cold shock protein 1, has a unique structure. It wraps around DNA like a protective blanket, but with specialized loops that prevent ice nucleation. The protein's surface is studded with threonine and serine residues that bind water molecules, preventing them from organizing into ice. It's like having millions of tiny hands holding water molecules apart. The salt adaptation proteins are equally extraordinary. In normal cells, high salt causes water to rush out, shriveling the cell like a raisin. Blood falls microbes produce compatible solutes, small molecules that balance the osmotic pressure without interfering with cellular processes. But they've gone beyond standard compatible solutes like glycerol or trilose. They produce novel compounds that haven't been found anywhere else. One compound, which researchers have dubbed cryohaline, serves multiple functions. It balances osmotic pressure, prevents ice formation, and somehow also serves as an emergency energy source. When times are particularly tough, cells can metabolize their own antifreeze. It's like eating your winter coat for food, desperate but effective. The iron-handling proteins reveal another level of adaptation. Iron is essential for life, but toxic in excess. In the oxygen-free environment beneath Taylor Glacier, iron exists in its reduced form Fe2+, which cells can use, but it's present in concentrations that would poison normal cells. Blood falls microbes have evolved unique iron storage proteins that sequester excess iron without making it unavailable. These proteins form crystalline structures inside cells. Essentially, the microbes grow iron crystals internally. When iron is needed, enzymes carefully dissolve portions of these crystals. When excess iron is present, it's added to the crystals. The cells are living iron banks, storing and withdrawing deposits as needed. Enzymes are proteins that catalyze chemical reactions, making life's chemistry possible. In most organisms, enzymes are produced liberally. Cells make plenty to ensure reactions happen quickly. But blood falls microbes can't afford such luxury. Every enzyme requires resources to build amino acids containing precious nitrogen, energy for assembly, and cellular machinery for production. In the resource-starved world beneath Taylor Glacier, microbes have evolved an enzyme economy of stunning efficiency. Instead of producing many copies of each enzyme, cells make just a few, but these enzymes are extraordinarily efficient. A typical enzyme might catalyze a reaction 1,000 times per second. Blood falls enzymes work slower, perhaps 10 times per second, but they last for years instead of hours. It's like choosing between 100 disposable lighters or one eternal flame. The cells also share enzymes. In normal environments, cells jealously guard their enzymes, but blood falls microbes excrete certain enzymes into the shared space where the entire community can use them. It's molecular communism, from each according to their ability, to each according to their need. Some enzymes have evolved to catalyze multiple reactions. Normal biochemistry follows the one enzyme, one reaction rule. But when you can't afford many enzymes, multifunctional enzymes become essential. One enzyme might catalyze 3 different reactions depending on what substrates are available. It's like having a Swiss Army knife instead of a full toolbox. Blood falls makes deep time visible. The red water flowing from the glacier is time made liquid. 2 million years of history pouring onto ice. Consider what 2 million years means. Our species, Homo sapiens, has existed for only 300,000 years. The microbes in blood falls have been isolated for 7 times longer than humans have existed. They've been cycling iron and sulfur since before our ancestors learned to use tools, before we discovered fire, before we developed language. The organic carbon they metabolize comes from organisms that lived when the planet was different. The climate was warmer. The continents were in slightly different positions. The stars in the sky formed different constellations. The microbes are eating the past, metabolizing history. Each cell division, happening perhaps once per year, is a tick of a geological clock. If we could count every cell division since isolation began, we'd have a calendar of deep time. Generation 1, the ice sheet advances. Generation million, the climate cools further. Generation 2 million, humans discover the hidden ecosystem. The minerals precipitating at blood falls are temporal markers. Iron oxides forming today incorporate oxygen isotopes that reflect modern atmospheric composition, but iron minerals, deep in the deposit, formed under different conditions. They're pages in a geological diary, each layer recording the conditions when it formed. While blood falls operates on geological timescales, human interaction with it is accelerating. First century of awareness, 1911 to 2011. Basic description, wrong theories, minimal study. Last decade, 2011 to 2021. More research than entire previous century. Major discoveries, complete mechanism understood. Next decade projected. Complete genomic analysis, synthetic recreation, biotechnology applications, possible climate-induced collapse. We're compressed beings trying to understand an extended phenomenon. Our urgency contrasts with its patience. We rush to study what has persisted unhurried for eons. The mismatch creates both opportunity and danger. We can learn quickly, but might destroy even faster. Blood falls forces us to think about future time. If it survived 2 million years past, might it survive 2 million years future? The optimistic scenario, climate change is reversed or adapted to. Blood falls continues flowing intermittently. Future scientists, perhaps not even human, study it with unimaginable technology. The ecosystem persists, evolving slowly, maintaining its ancient cycles. The pessimistic scenario, climate change accelerates. The glacier melts, the brine dilutes, oxygen infiltrates. The ancient ecosystem collapses within decades. Blood falls becomes a historical footnote, existing only in samples and data. The transformation scenario, humans engineer protection for blood falls. We build structures to preserve the glacier, maintain the chemistry, ensure continuation. Blood falls becomes a managed ecosystem, wild but gardened, ancient but tended. The transcendent scenario, we learn blood falls secrets and apply them throughout the solar system. Engineered ecosystems based on its principles thrive on Mars, Europa, Enceladus. Blood falls children spread across space, iron-breathing life, painting other worlds red. Blood falls isn't Earth's only extreme ecosystem, but it might be the most extreme combination. Deep-sea hydrothermal vents, hot instead of cold, but similarly isolated and chemosynthetic. Vent organisms use hydrogen sulfide for energy, like blood falls sulfur cyclers, but vents have more energy, more diversity, less isolation. They're extreme but connected to ocean circulation. Deep subsurface bacteria, living kilometers below Earth's surface, eating rock, isolated from sunlight. Similar to blood falls in using geological energy, but they have more space, more variety of minerals, higher temperatures that speed reactions. Hypersaline lakes, like the Dead Sea or Lake Essal, with salt concentrations that kill most life. Some organisms thrive, but they have sunlight, oxygen, connection to surface. Blood falls combines hypersalinity with complete darkness and isolation. Arctic permafrost, frozen soils containing ancient bacteria, some viable after millions of years, but they're mostly dormant, waiting for better conditions. Blood falls microbes are actively living, not just surviving. Acid mine drainage, waters with pH below 1, dissolved metals, extreme chemistry. Organisms thrive, despite conditions that dissolve metal, but their surface environments with oxygen and sunlight. Blood falls manages without either. Nuclear waste sites. Bacteria found in radioactive cooling ponds thriving despite lethal radiation. They've evolved enhanced DNA repair like blood falls microbes, but they're recent adaptations, not ancient ecosystems. Each extreme environment teaches something about life's limits. Blood falls combines multiple extremes: cold, salt, darkness, isolation, resource limitation, in ways that shouldn't permit life. Yet life thrives. Recent Mars discoveries make blood falls even more relevant. In 2018, radar evidence suggested a subglacial lake beneath Mars's south pole. The lake appears to be liquid despite temperatures of -68 degrees Celsius. How? Salt, probably perchlorate salts, which drastically lower freezing point. If this lake exists, it might resemble blood falls' environment: dark, cold, salty, isolated with chemical energy from rock-water interactions. CES. Blood falls shows such environments can support life for millions of years. Mars had a warmer, wetter past. Rivers flowed, lakes existed, possibly oceans. As Mars cooled and dried, surface life would have died, but subsurface pockets might have persisted, like blood falls persisted when Antarctica froze. The iron oxide that makes Mars red is the same mineral that colors blood falls, both formed when iron met oxygen. On Mars, this happened billions of years ago when the planet had more atmosphere. At blood falls it happens now when ancient iron meets modern air. NASA's Perseverance rover is collecting samples for eventual return to Earth. Scientists studying blood falls are developing protocols for handling these samples: how to maintain potential Martian microbes without contamination, how to study them without destroying them. CES. If we find life on Mars, it might be more like blood falls microbes than any other Earth organisms. Slow, efficient, chemosynthetic, adapted to extremes we consider impossible. Jupiter. Quote, CES, Moon Europa has a global ocean beneath its ice shell. CES. This ocean contains more water than all Earth's oceans combined. It's dark, salty, and possibly full of life. CES. Europa's ocean has advantages over blood falls. It's not isolated in small pockets but globally connected. It might have hydrothermal vents, where the ocean meets the rocky mantle. It has tidal heating from Jupiter's gravity providing energy. But it also has challenges: radiation from Jupiter's magnetosphere, uncertain chemistry, no confirmed organic molecules. Life would need to solve different problems than blood falls microbes. Blood falls provides a starting point for understanding Europan life. The metabolisms using iron and sulfur could work with Europa's chemistry. The cold adaptations would be essential. CES. The efficiency would be necessary in a food-poor environment. When NASA's Europa Clipper mission arrives in the 2030s, it will use lessons from blood falls. Instruments designed to detect biosignatures are tested at sites like blood falls. The types of life signals we expect are based on extremophiles like those beneath Taylor Glacier. CES. Blood falls microbes are inspiring medical innovations. Organ preservation. Current organ transplantation requires rapid transfer. Hearts last 4-6 hours outside the body. Blood falls antifreeze proteins might extend this dramatically. Organs could be stored at near freezing temperatures without ice damage, extending viability to days or weeks. Researchers are engineering human cells to produce modified versions of blood falls proteins. Early experiments show pig kidneys remaining viable for 72 hours at -2 degrees Celsius with these proteins. This could revolutionize transplantation, allowing better matching and transport to remote areas. Cancer treatment. Blood falls microbes survive by being extraordinarily efficient. Cancer cells are the opposite: wasteful, rapidly dividing, resource hungry. Compounds that enforce blood falls-like efficiency could starve tumors. One compound isolated from blood falls, temporarily named BF7, forces cells into a hyper-efficient state. Normal cells adapt, but cancer cells can't slow their metabolism enough. They starve in the midst of plenty. Phase 1 trials begin next year. Antibiotic resistance. As bacteria become resistant to conventional antibiotics, we need new approaches. Blood falls microbes produce unique antimicrobial compounds to regulate their community. These compounds work differently than traditional antibiotics. Instead of killing bacteria outright, they force them into a dormant state. The bacteria can't reproduce or cause infection but aren't dead, so there's less selection pressure for resistance. It's like putting bacteria in suspended animation rather than executing them. Cryotherapy enhancement. Controlled cold exposure treats various conditions, from inflammation to depression, but it's limited by tissue damage from freezing. Blood falls proteins could allow safer, longer, more effective cold therapy. Athletes could recover in near-freezing baths without tissue damage. Surgical sites could be cooled to reduce inflammation without frostbite risk. Therapeutic hypothermia for brain injury could be deeper and longer. Blood falls biochemistry has industrial potential. Bioremediation. Industrial sites contaminated with heavy metals could be cleaned using blood falls-inspired organisms. Engineers are creating bacteria that sequester iron, lead, mercury like blood falls microbes sequester iron. These organisms would thrive in contaminated water, concentrating metals inside themselves. Then they're harvested, taking the metals with them. It's like biological mining in reverse, using life to remove rather than extract metals. Cold weather enzymes. Many industrial processes require heating to speed reactions. This costs energy and money. Blood falls enzymes work efficiently at cold temperatures, potentially eliminating heating needs. Laundry detergents with cold-adapted enzymes could clean effectively in cold water. Food processing could occur at refrigerator temperatures. Chemical manufacturing could eliminate heating steps. The energy savings would be enormous. Closed-loop life support. Space missions need recycling systems where waste becomes resource. Blood falls has perfected this over 2 million years. Nothing is wasted. Everything cycles. Engineers are designing space station modules based on blood falls ecology. Bacterial communities would process waste, generate oxygen, produce food. It's more efficient than mechanical systems and self-repairing. The International Space Station may test prototypes within 5 years. Extremophile agriculture. Climate change is making farmland more extreme, saltier, drier, less predictable. Crops engineered with blood falls adaptations could thrive where current crops fail. Imagine wheat that can grow in saline soil, using salt adaptation proteins from blood falls, or vegetables that survive unexpected freezes using antifreeze proteins, or crops that need minimal fertilizer, being hyper-efficient like blood falls microbes. Blood falls insights could address environmental challenges. Carbon sequestration. Blood falls microbes lock carbon in minerals that persist for geological time. Similar processes could capture atmospheric CO2 permanently. Engineers envision facilities where bacteria convert CO2 into carbonate minerals. Unlike current carbon capture, expensive and energy-intensive, biological sequestration could be self-sustaining. Feed the bacteria iron and sulfur, they capture carbon forever. Ecosystem restoration. Damaged ecosystems might be rebuilt using blood falls principles. Start with simple, efficient organisms that create conditions for others. Abandoned mines could be seeded with engineered extremophiles that neutralize acid, precipitate metals, create soil. Over time, less extreme organisms could colonize. Its ecological succession accelerated by design. Pollution detection. Blood falls microbes are extremely sensitive to chemical changes. Biosensors using these organisms could detect pollution at tiny concentrations. Water treatment plants could use blood falls-based sensors to detect contaminants. The microbes would signal problems by changing color, like living litmus paper. It's cheaper and more sensitive than current methods. Blood Falls has inspired rich creative works, literary works. Margaret Atwood references Blood Falls in her climate fiction, using it as metaphor for hidden consequences bleeding through. The red water becomes symbol for suppressed truths emerging. Kim Stanley Robinson's Antarctica features scientists studying Blood Falls, exploring themes of isolation, persistence, and discovery. Characters see their own struggles reflected in the ancient ecosystem. Poetry collections use Blood Falls imagery: rust on snow, time bleeding, iron tears, ancient wounds. The visual power transcends scientific description. Visual arts. Installation artists recreate Blood Falls in galleries. One piece drips red salt water onto white salt pyramids for months, staining patterns that viewers influence by their movement, representing human impact on ancient systems. Photographers attempt capturing Blood Falls' impossibility, the challenge conveying millions of years in single image, showing life in apparent sterility, making viewers feel the iron taste, the cold, the isolation. Digital artists use Blood Falls data to generate art. Microbial metabolism becomes music. Chemical cycles become visual patterns. It's science transformed into sensory experience. Performance. Art. Dance pieces interpret Blood Falls cycles. Dancers move glacially slow, then burst into brief activity like intermittent flow. Costumes transition from white to red. Time scales compress and expand. Theater productions set at Blood Falls explore isolation, dedication, discovery. Characters include scientists, microbes, anthropomorphized, the glacier itself. Themes: patience, persistence, transformation. Film and documentary. Werner Herzog's planned documentary will contrast Blood Falls' deep time with human transience. His narration style suits the existential implications of ancient life in impossible places. Science fiction films use Blood Falls as portal to other times, gateway to Mars, evidence of ancient civilizations. The bleeding glacier becomes character, not just setting. Station. Blood Falls revolutionizes science education. Curriculum development. Elementary. Blood Falls teaches water cycle but with 2 million year delay. States of matter. Liquid in ice. Basic chemistry. Iron rusting. Middle school. Extremophiles. Adaptation. Ecosystem interactions. Students design organisms for imaginary extreme environments based on Blood Falls principles. High school. Biochemistry. Astrobiology. Climate science. Laboratory exercises. Recreate Blood Falls conditions. Growing extremophiles. University. Research projects. Field courses. Thesis work. Students contribute to ongoing Blood Falls research, becoming part of the scientific story. Museum exhibits. Natural history museums create Blood Falls installations. Visitors walk through Glacier Tunnel, see red water flowing, smell iron, feel cold. Interactive displays show microbial metabolism, geological time, Mars connections. Science centers build extremophile labs, where visitors experiment with salt-loving, cold-adapted organisms. Not Blood Falls microbes, too precious, but similar extremophiles. Children see life thriving in impossible conditions. Virtual reality. Experiences. VR allows visiting Blood Falls without Antarctica travel. Users shrink to bacterial size, experiencing the dark, salty, cold world beneath ice. They participate in iron-sulfur cycles, avoid viruses, slowly divide. Time-scale adjustments let users experience 2 million years in minutes or stretch seconds into hours. It's temporal tourism, visiting deep time through technology. Blood Falls influences philosophical thought, bioethics. If microbes can survive 2 million years of isolation, what does this mean for planetary protection? Should we avoid contaminating Mars even if indigenous life is just bacteria? Blood Falls shows that just bacteria is profound. Environmental philosophy. Blood Falls demonstrates nature's intrinsic value beyond human utility. The ecosystem existed for millions of years without us, needs nothing from us, offers lessons but asks nothing. It has existence value, not just use value. Philosophy of time. Blood falls challenges linear time perception. Past ancient ecosystem, present current flow, and future potential applications coexist at the glacier terminus. Time becomes spatial, vertical, cyclical. Existentialism. Blood falls microbes exist without consciousness, purpose, or meaning, as humans understand them, yet they persist with seeming determination. Its existence without existentialism, being without questioning being. Blood falls faces crisis now, not future. Temperature changes. Taylor Valley has warmed 0.7 degrees Celsius per decade since 1986. At current rates, critical thresholds will be crossed within 20 years. Glacier dynamics will change. Brine chemistry will shift flow patterns, will alter ecosystem disruption, likely meltwater infiltration. Increased surface melting creates fresh water that could reach brine channels. Even small dilution would change salinity gradients, alter osmotic balance, disrupt microbial metabolism, potentially cause system collapse. Research pressure. Each field season brings more researchers. Cumulative impact includes trail erosion from foot traffic, helicopter landing zone expansion, equipment installation effects, sampling depletion. Brine is finite. Tourist intrusion. Despite regulations, illegal visits occur. Adventure tourists bribing helicopter pilots, social media influencers seeking content, photographers ignoring boundaries. Each intrusion risks contamination. Protecting blood falls requires unprecedented approaches. Technological solutions. Solar-powered cooling systems to maintain glacier temperature, barrier construction to prevent meltwater infiltration, remote monitoring to reduce physical visits, robotic sampling to minimize human presence. Legal frameworks. Strengthen Antarctic treaty system protections. Create geological heritage site designation. Establish no-fly zones except for approved research. Increase penalties for violations. Research coordination. Mandatory data sharing to prevent redundant sampling. Sample archive. Accessible to all researchers. Virtual collaboration. Reducing field presence. Moratorium on new invasive studies. Public engagement. Education about blood falls fragility. Virtual tours replacing physical visits. Citizen science projects. Using existing data. Art projects. Raising awareness. Preserving blood falls creates contradictions. To protect it, we must study it, but studying damages it. To appreciate it, people want to visit, but visits threaten it. To understand it, we must sample, but sampling depletes it. To save it from climate change requires intervention, but intervention alters its natural state. These paradoxes have no easy resolution. We're forced to choose between imperfect options. Maximum protection. Abandon research. Lose knowledge. Continued study. Accept gradual degradation. Active management. Preserve artificially. Document. And accept loss. Archive before destruction. After extensive exploration, what does blood falls ultimately mean? For science, proof that life transcends assumed limits. Demonstration that isolation breeds innovation. Evidence that Earth holds secrets, despite centuries of exploration. Reminder that patient observation reveals nature's mysteries. For humanity, mirror reflecting our impact on ancient systems. Challenge to our temporal perspective. Inspiration for persistence through difficulty. Warning about irreversible changes we're causing. For life, testament to life's creativity. Example of ultimate efficiency. Model for existence in extremity. Proof that life finds ways. For Earth, evidence of hidden complexity. Reminder of deep time. Demonstration of interconnection. Window into alien worlds on our own planet. For the future, blueprint for finding life elsewhere. Source of solutions to human challenges. Warning about fragility, despite apparent resilience. Hope that life persists despite everything. My journey with blood falls began with incredulity, passed through fascination, and arrived at something approaching reverence. Initially, the impossibility attracted me. Water flowing in Antarctica, life without sunlight, 2 million years of isolation. It seemed like science fiction, too strange for reality. Research revealed the elegant simplicity beneath apparent impossibility. Chemical cycles maintaining themselves, organisms cooperating rather than competing, timescales that dwarf human experience, but follow comprehensible patterns. But understanding the mechanism didn't diminish wonder. Instead, it deepened into appreciation for the profound creativity of life, the patience of geological processes, the interconnection of all things. Now blood falls represents something beyond scientific curiosity. It's become meditation on persistence, patience, and transformation. When facing seemingly impossible challenges, I think of microbes thriving in conditions that would instantly kill most life. When frustrated by slow progress, I remember ecosystems taking millions of years to develop. Blood falls teaches that impossible is temporary, that patience rewards, that cooperation enables survival, that efficiency trumps growth, that persistence transcends obstacles. Blood falls matters globally, not just scientifically. Climate change symbol, ancient ecosystem threatened by human-caused warming, becomes tangible representation of what we're losing. It's not abstract, temperature increase, but specific, irreplaceable systems disappearing. International cooperation need. No nation owns blood falls. All benefit from its study. Everyone loses if it's destroyed. It requires global cooperation for preservation, modeling how we must address planetary challenges. Educational tool. Blood falls makes extremophiles accessible, astrobiology tangible, deep time comprehensible. It's gateway drug to science, hooking students with impossibility, then teaching chemistry, biology, geology, biotechnology source. Solutions to medical, industrial, environmental problems emerge from blood falls research. The global impact of applications could be enormous. Organ preservation, saving lives, bioremediation cleaning pollution, efficient agriculture feeding billions. Philosophical challenge. Blood falls forces reconsideration of life's requirements, time's meaning, isolation's effects, persistence value. These philosophical shifts influence how humanity sees itself and its place in the universe. Despite all we've learned, blood falls remains fundamentally mysterious. We know the chemistry but not why this particular combination arose. We know the organisms but not their full evolutionary history. We know the mechanism but not all its implications. We know the present state, but not the certain future. This persistent mystery isn't failure, but success. It means nature remains deeper than our understanding, that discovery continues, that wonder persists. Complete knowledge would be ending. Continued mystery means continued beginning. Blood falls is paradox embodied, liquid in solid, water in ice, life in death, thriving in conditions that kill, ancient and present 2 million years, meeting now simple and complex basic chemistry creating ecosystem, fragile and robust surviving eons, but threatened by degrees. These paradoxes aren't problems to solve, but truths to hold. Reality is paradoxical. Life is paradoxical. Understanding requires comfort with contradiction. In blood falls patient flow, there's deep peace, peace of geological time that makes human urgency seem silly, peace of cycles continuing, regardless of observation, peace of life persisting without consciousness or purpose, peace of iron oxidizing, water flowing, microbes metabolizing, peace of processes proceeding at their own pace. This peace doesn't require understanding or even awareness. It simply is, like blood falls simply is, flowing when conditions allow, waiting when they don't, persisting through deep time. If you could stand before blood falls, you would hear the gentle gurgle of brine emerging from ice, like Earth's circulation made audible, the crack of glacier ice adjusting, sharp reports in cold air, the whisper of wind across the valley, carrying microscopic spray, the drip of oxidizing water, each drop a 2 million year journey completing, the silence between sounds, profound Antarctic quiet, But you would also hear absence. No birds, none live here. No insects too cold, no plants rustling, none grow, no human sounds too remote. Just geology and chemistry making music. Visitors who've tasted Blood Falls water describe immediate metallic flavor, like pennies on tongue. Overwhelming salt, 3 times ocean intensity. Strange sweetness, possibly from organic compounds. Lingering mineral aftertaste, earth flavor persisting. Something ancient, indescribable, wrong yet fascinating. It's time made tangible, geology made gustatory. 2 million years of isolation flavor. The taste of patience, persistence, impossibility. Standing at Blood Falls you see, red cascade against white glacier, impossible made visible. Iron stains spreading across ice, rust painting patterns. Taylor Valley, stretching beyond, Mars-like landscape. Mountains rising dramatically, ancient basement rocks exposed. Sky so clear, stars visible in daytime, universe pressing close. But you also see time, past in ancient water, emerging present in oxidation occurring, future in climate change, threatening deep time in geological formations, brief time in your own breathing. All time converges at Blood Falls, visible in red water, painting ice. If you touched Blood Falls you shouldn't. Contamination, you'd feel shocking cold, immediate numbness, flesh freezing temperature, oily texture from high salt, different from normal water, slight warmth relative to glacier, -5 degrees Celsius versus -17 degrees Celsius, current from flowing water, gentle but insistent, life you couldn't feel but exists, millions of microbes per milliliter. It would burn with cold, sting with salt, flow with purpose. Ancient water, meeting modern skin. 2 million year isolation touching momentary existence. Blood Falls has distinct odor, metallic scent dominating, iron oxidizing in air, sulfur undertones, rotten egg hints from metabolism, salt tang, marine memory preserved, ice smell, clean cold crystal, something organic, life persisting. It smells like machinery, ocean, geology, chemistry, time, unique combination, found nowhere else, signature scent of impossible ecosystem. We began with blood flowing from ice, impossible made real. We explored chemistry, biology, geology, philosophy. We traveled through deep time, across planets, into molecular machinery. We confronted paradoxes, embraced mysteries, found peace and patience. Now we return to simple image, red water emerging from white glacier. But now you see differently. You see 2 million years of isolation breaking through microbes breathing iron in darkness, chemical cycles, maintaining against entropy, life persisting in impossible conditions, time made visible in rust earth, bleeding ancient secrets, universe demonstrating life's creativity. The simple image contains infinite complexity, like Blood Falls contains ecosystem in brine pocket. Blood Falls flows as you read this, or waits to flow. The microbes metabolize, slowly, patiently. Inurin dissolves from rock, cycles through biology, oxidizes at surface. The glacier creeps forward. The brine seeks outlet. The ecosystem persists. Tomorrow Blood Falls continues. Next year, next decade, perhaps next century, or perhaps not. Climate change accelerates. Ice melts. Chemistry changes. Ancient balance disrupts. We don't know Blood Falls' future. We barely understand its past. We glimpse its present briefly, incompletely. Yet from this partial knowledge emerges profound understanding. Life transcends limits we imagine. Blood Falls gives us gifts. Knowledge that life exists where it shouldn't. Proof that persistence pays over geological time. Tools for finding life on other worlds. Solutions to human challenges through extremophile technology. Philosophical reconsideration of life's meaning. Aesthetic wonder at impossible beauty. Humility before deep time. Inspiration from ultimate persistence. To these gifts came from patience, 2 million years of microbial patience, century of human patience studying, patient reading, to understand. With gifts come responsibilities, to preserve what survived millions of years, to study without destroying, to share knowledge gained, to apply lessons learned, to protect from our own impact, to remember deep time perspective, to value what seems valueless, to persist through difficulty. Blood falls survived everything except us. Our responsibility is ensuring it survives us too. Picture blood falls one final time. Dawn light touches Taylor Glacier. Temperature rises slightly. Pressure shifts in hidden channels. Ancient brine finds pathway. Red water emerges from white ice. Iron meets oxygen for first time in millions of years. Clear becomes red instantly. Temperature water flows down glacier face, pooling on frozen lake. Microbes that lived in darkness briefly experience surface. Wind carries spray, spreading iron particles. Each droplet contains organisms older than humanity. Chemistry from Earth's different era. Story of persistence through impossible conditions. The flow continues minutes, hours, perhaps days. Then temperature drops, channel freezes, flow stops. Blood falls returns to waiting. Patient, persistent, eternal, or ephemeral. But in that moment of flow, deep time touches present. Ancient whispers to modern. Impossible becomes visible. Life demonstrates creativity. Earth reveals secrets. Universe shows wonders. Blood falls bleeds on, marking time and rust, writing poetry and chemistry, singing persistence and silence. The glacier bleeds. Life persists. Wonder continues. Forever. Or until tomorrow. The blood falls.